And this conference started in the 70s. And it was the first conference in robotics. And many colleagues from Russia, from the Soviet Union at the time, and from the Eastern countries were meeting with the West. And it was like that meeting that was between Italy, actually, in Udine most of the time, and Warsaw. And I had the opportunity to participate in this meeting in the early days, and we decided to come for the 20th edition, so almost 40 years from the start of that meeting, because it's held every 2 years, to Moscow. And we just finished this meeting, and then we had this invitation. Thank you very much for this opportunity. Thank you very much for also being here, because it seems like we have a broad range of different robotic interests. I'm going to talk. I'm from Stanford University, from the Artificial Intelligence Laboratory, and I personally graduated from France. Donc je peux parler français. On peut faire la présentation en français, but I will switch to English. I think it's more. But I'm going just to talk about really what is happening in robotics today, and how exciting things are in robotics. So we are celebrating 50 years of robotics. You can see the first robot that was built, called Unimate. That was the date when we marked the beginning of industrial robotics. And then, since then, many robots were built, and many different systems were developed. But essentially, robotics is coming to maturity, and the maturity of robotics is well viewed in industrial applications. We have millions of robots operating around the world today, and those robots are not only just results of research, but they are really also results of integration with manufacturing. We understood how to integrate the robotic system in a manufacturing process, what to do to make it efficient. And this success, in fact, is now behind us, because robotics moved beyond manufacturing. Robotics is moving beyond manufacturing, and we started to see many different new application areas. The thing about robotics today is that we are moving to the human environment, so we are moving outside of the manufacturing environment, which is a structured environment. We are moving to an environment that is completely unstructured. We have the human in that environment. We need to interact with the human, and that's why we need social robotics. That's why we need to interact with the human in understanding actually the model of the human. So we need to augment the human. We need exoskeletal systems. We see a lot of things happening around the human. The robotic revolution, probably one of the most striking result of what we are seeing today, is in medical robotics. In medical robotics, we are able now to perform operations on human without opening the body. Through small incisions, we are putting the robot, and the surgeon is fortunately still there. The surgeon is operating from outside. This means a very efficient way of taking a patient, doing the operation, and letting the patient go home very fast. That is, the patient is not going to have the trauma of the post-operation. And this technology is now performing 40,000, 60,000 operations regularly. Stanford Hospital is performing this in Europe. Everywhere we have those almost standard operations. Now, this idea, if you look here, you see the hand of a surgeon, an expert, touching and controlling a machine that is a little bit remote, just maybe in the next room. This concept is very close to the concept that is now being promoted in the European Union, and in a lot of projects that brought a large number of groups from Europe and in the US to create something we call the robot companion. The robot companion actually is a proposal that was very close to winning large support from the European Union, and that brought a lot of ideas about where to apply robotics, bringing a lot of different groups from all Europe. And that is that idea is now being pursued in the Horizon 2020 through a new program, a new project. This is really interesting. There is Robotics now, and a lot of new companies in the US are investing in robotics. So this is, sorry, this slide should be before Horizon 2020 and the new program that is also supporting the company. Google, we started from my lab. Actually, the founder of Google, one of them is Russian, the other one, Page, was a student working in my laboratory, and he was interested in robotics, but fortunately he decided to do search. So he decided to do search, and they came up with the idea of Google. But interestingly, Google is now coming to robotics, back to robotics, because we can talk about, maybe you can ask me why they are coming to robotics and why all these companies are really now ready to invest and put an effort in those machines. So we were in the digital knowledge. Now we are going to the physical processing and the interaction with the human. And this is a very interesting aspect. I want to start talking about the technology by showing you a short video of my students, what our students are able to do today. And this is work that is done in class. It's not research. This is what the student, so this is related to education. I mean, how we do educate our students to do things. So the robot is fighting with the student, and this is done through understanding what the student is doing, planning attack, planning defense, perceiving the environment, and developing a controller that allows you to interact in real time with the human. And what is interesting is that the students are doing this project in 3 weeks. So 3 weeks means that they really have the knowledge, that is the theory, but then also they have the infrastructure of software, environment, and hardware and processing to be able to do it.
Is it based on computer vision?
Well, so this is actually done with a Kinect to find the depth, and then it's connected with an environment that we developed. It's called Psi, and this is a product that we developed to control robot, and we will talk about it a little later and understand the human motion and do all these things. So robotics, which started in industry, initially we oversold robotics. We said robotics will solve everything, and we will change the industry. And in fact, it was a mistake, because a long time ago robotics wasn't ready. But now robotics is ready because computer technology, material fabrication, the intelligence, the maturity of the field, the algorithms, everything, the perception, all of these things are now ready to take us to the new frontiers. And the new frontiers of robotics is the intelligent robot system. But what is the frontiers? So someone was talking about mining here. Now in mining, it's not only vehicles, it's not only moving things. It is a lot of work that is done by human, and those humans are down there, and we have a lot of accident. We had accident in mining in Turkey. We had accident in mining in South Africa. We have accident in mining in Chile, and we want to take these people from the bottom of the mine and take them. We need their skills, but can we make them work without being there physically? Can we make them work like what we are doing in surgery? So we go and do surgery under the ground. Archaeology. can we go and do archaeology underwater, not only with the moving and observing and looking, but really do the work that is touching the environment, scratching and taking the object and manipulating the object? Can we do inspection and maintenance of pipelines underwater in the better oil platforms? Can we do that? Can we deal with disastrous areas like Chernobyl or Fukushima and all these challenging areas where robots can do more than just looking? We do not want robots to be just observing. We made a lot of progress in mobility, but can we go to the environment and do things in the environment? So here is the concept, and I will develop the concept later. You see, this is my student, and my student is now working with a device we call haptic device. The haptic device allows the students now to interact with a robot that is down in the ocean. So the robot is down, but the human can touch and feel what the robot is touching. And now you can do operations underwater. This robot is being developed currently, and we will talk about this project. This robot is now under the control of the human, but the robot has a lot of autonomy. That is, the control of the robot is done by the robot. The human is guiding, giving goals to the robot and specifying where to go and when it needs to touch. It's like surgery underwater. It is the same concept, but now the surgery is much more efficient because now we are able to feel. In most of surgical robots, we do not feel the feedback, we only see. Now we can see in 3D, and we can touch, and then we can feel the contact, and then we can start the manipulation. This is full dynamic simulation underwater with the dynamics of the water and the interaction with the water and the guidance of the human. Very, very advanced, high-level guidance of the human. And now we can close this valve, and then we can move to the next task, and the human is interacting with those things. So let's look at technology today. This is Ashimo. Everyone knows Ashimo, right? This is Honda. So Ashimo is hopping, Ashimo is running. It's amazing. But we have made a lot of progress in free space. The question is, can we do anything useful with Ashimo? Can we get Ashimo finally to interact with the world? Can Ashimo touch, take an object and open it and place assemblies together and do those things? This is very difficult. The question of going beyond mobility is very hard because it requires a different way of control, a different way of thinking. It requires touching the environment. Touching is very difficult for robots. And multi-contact robot is very, very hard. So we need to think differently about how to deal with those tasks. Look, Ashimo is doing this task. And the question is, when Ashimo is performing this task, this is what we want Ashimo to do. The reality is, this task is pre-programmed. And how much programming, how much time we spend programming this robot? Enormous amount of time. And if we change anything in that environment, the robot will be confused and will not be able to do it. Because this robot is programmed to move every joint exactly in the same way to reach that object, and exactly in the same way where the cat of the bottle is located. So the challenge is, can we eventually someday do it like this little boy, or do it like that artist there? How can we take those skills from the human and somehow map them to the robot so that the robot can become skillful? Sometimes not only skillful, almost expert. These people are using their hands in very delicate things. What is the secret there? How can we unlock those secrets and understand what is happening? This is the key to taking robotics to the next stage. The ability of manipulating the environment with the hands of the robot and being able to understand what are those skills. The human are amazing. Human are just unbelievably amazing models for robots. And we really need to understand the human in order to really develop the right robotic systems. Otherwise, we will spend our time programming the robot and reprogramming the robot, and the robot will be always failing. So, first of all, we need to model the musculoskeletal systems. We need to model this very complex system in ways that allow us to understand motion. The question is not to reproduce every single motion. We need to understand what is the strategy, what is behind the motion. And that is something that requires deeper understanding, modeling, and capturing the essence of the motion. We need to understand the skills. We need to understand the skills that is not to copy one skill of putting an object on the table. We need to understand what is the strategy. What is the strategy goes to something more abstract about compliance, about the center of compliance. So when we interact with the robot, this is a haptic device interacting with the robot. The robot is going to touch the environment. The human can teach the robot how to do it, and the robot extracts that strategy. And once we extracted the strategy, the robot can perform that strategy in real time. So skills requires analysis of the skills and understanding of the compliant relations between the robot, the environment, the perception, the tactile information that is being used, and then we can start to interact with the environment like humans do. Humans make use of a lot of things. So when we are performing a task, we brace, we use contact, we use multiple contact. Our body is in contact. It's not just we move to a location and grasp an object. There is a whole body interaction. Exactly. That's what you... And when we do that, there is something very challenging about that interaction between all these different points of contact with the environment. And we really need to understand that. We need to understand the reaction forces we're producing. We need to understand the interaction in terms of internal forces we are producing, how we are grasping the environment. When we touch the environment, actually we are hugging the environment and attached to that environment. The way we balance forces, the way we balance the body is very, very important. So here is what happened when we understand it. Ashimo is performing something that Ashimo never in its imagination can perform. I don't know if any one of you have seen a show of Ashimo. They say when you come to the show of Ashimo, we had a show in Italy, and the first thing they tell you at the show, there is one rule with Ashimo. Only one rule. Do not touch it. Do not touch the robot. Because the robot is programmed to move every joint to perform that motion. And if you touch it, immediately it goes unstable. So,
and I can tell you another thing. I was in Japan invited to the Asimov, and he was moving with the children, kissing the children. But I saw a man with a written Honda staff, with a black shirt on the top of the hall. I wanted him and said, "What are you doing?" He was Japanese. He was doing with microphone, saying, "Move up, down," and the robot was following the motion. And it was, I remember the day, it was 10 September 2001. It was the day before that they made the planes in the towers in New York. And the evening, the day before, we were meeting with Japanese friends. And they say, I told them, but it's not robotics really, it's telerobotics. And they told me, Alberto, did you really think that he was a robot? And repeat slowly, did you really think that he was a... So he said, yes, I thought. So, really is completely telecontrolled.
Yeah.
I remember that year. Maybe today, no. But
well, yeah. Well, I mean, in the last.
Excuse me, the interruption.
No.
You called me, looked at me, and so I'm saying.
No. I know, Roberto. This is very important. I think in the last 11 years, I've been working with Ashimo. I have 2 Ashimos at Stanford, and we took Ashimo to Stanford to to teach Ashimo how to do. So Ashimo is a student, and he will eventually graduate from Stanford University. So Ashimo is learning how to make contact and follow the guidance of the human. This is almost surprising to Ashimo. Actually, you can see Ashimo very surprised. What's going on? What is happening to me? Oh, okay, all right, I follow you. So this is a basic thing we call compliance, the ability of the robot to feel the forces of the human and to follow its motion. The robot has force and tactile perception and is able now to move and follow the guidance of the human. Now we can teach the robot how to touch and lift objects. And all of this requires a different way of control. The control is not anymore a control of trajectories. We do not program the trajectory. Look at the hand of the human. The human hand is coming and the robot is instructed, don't touch my hand. And when the hand of the human comes, the robot moves away and open the way for the hand to move. This ability of feeling, seeing, understanding the interaction is very, very important. And for robots like Ashimo, this is something that was not at all in its brain. All what we taught Ashimo was control trajectories of the joints, and just you do it pre-program and then you move. So Ashimo now is capable of doing much better than before, but there is another dimension of this is the technology, the hardware. What is required in the technology in terms of sensors, actuation, torque control, all of these architectures that are needed for the system. I have a lot of details, but just for the sake of time, I'm going to talk about two major projects. And these projects will illustrate a little bit the direction of research that is taking place. The first one is the problem of taking robotics to dangerous areas in the field and thinking about, instead of having a human going in that environment, how can we replace the human with a robot? Now we can think about this by saying, let's take a quadruped robot, a walking robot, and put arms on it and do all of that and try to go inside those environments. But those environments are very narrow. There are very narrow passages. You need to do manipulation. You need to do perception. Humanoids are amazing because they are very compact. And humanoid could be the solution, but humanoids are today unable to go there because they are designed for flat indoor environment. So they can walk on the flat environment, and they cannot deal with any challenging three-dimensional environment. So how can we change that? If we change that, then we can move to those challenging environments. How can we change that? To change that, we need those technologies that we developed for contact. Because if we are able to do contact-supported locomotion, we can do contact-supported whole-body control. The robot can move like a human and use the environment to support itself. So that requires us technically to be able to control contact forces. On the left, you see what will happen if you are not careful about it. The robot will just collapse. On the right-hand side, you see what happens if you are able to control contact forces. When you control contact forces, you are going to be maintaining those forces despite earthquakes, moving the environment, whatever problems you have. You need to be able to control these internal forces. And we are illustrating how we can do that work. This is a very challenging problem in robot control that requires sensing, that requires understanding of the environment. So we need to detect friction. We need to deal with the slippage when slippage happens. We need to deal with disturbances. This has to be robust. So if these blue things are forces, we're hitting the robot with those disturbances, and the robot still maintaining the forces. And this is very, very important, the robustness. We are now able to detect friction and get a robot to climb even backward. Can you do it? Can you do this?
I think so.
You can do it. Good. the robot can do it too. So now we are able to do human-like skills with multiple contact and multiple. This is actually very, very new. It's not even published. I mean, right now we're working on those technologies of taking humanoid robotics to the next level, to the level where we can interact with those environments. So this is in the home. If you are touching, if you are, it is you.
Ой.
We cannot stop it.
Не спеши, не спеши.
Music pause.
Oh, okay.
Может, мы все
no
повыключаем
problem.
звук так, на всякий случай? Как в кинотеатре.
Yeah. So you can see here the robot using those multi-contact to support its movement and also to perform the task. Now, sometimes in those dangerous environments you don't have, in fact, you do not have the ability to support with any contact. So you take the contact with you, like skiing. So now we created what I call supraped. The robot is biped. You can do triped, quadruped, and now you can go to an environment where you increase the supporting area. So to do that, what we need to do is to understand. I realize I have to explain one more point here. We need to understand. We need to understand that. Yeah. Where is the field?
F5.
F5? I think so.
No.
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 You have another.
Home?
No, because my okay. No, I wanted to go back to the projection show slide. so
And
so
now it's back.
yeah. So what we need to do is to take this analysis of the motion and integrate it in the robotic system. Otherwise, you motion capture the human, you analyze the muscular properties. Oh, by the way, this is my student. She's from Moscow, a Russian student. And you start analyzing human and look at how human perform those motions. And what you discover is that human actually make use of the same thing that we use when we build machines. They make use of the mechanical advantage. In the case of human, it's physio-mechanical advantage, which gives us the rules and the characteristics of the motion, which allow us to basically understand what is behind those characteristics that are being used in motion. So if we are drinking water, the question is, why do we drink with our arm in this configuration and not in this configuration and not in that configuration? There is a secret. It relates to the effort being exerted, the gravity. And in fact, when you drink, there is almost, for everyone, 42 degrees. And this is due to the fact that we are minimizing the effort. So humans minimize the energy associated with their muscles and weighted by the capacity of the muscles. So the energy that we minimize is equal to a constant C associated with the capacity of the muscle and the square of the muscles. And that energy is equal to Cm squared.
Yes.
What?
Yes.
Yes? Have you seen this before, equation?
Connection in
In the
degree
energy.
too.
Yes. Actually, this is seriously true, because with Cm squared, you can see if you are pushing something, very heavy, you push it from the right with no effort, because you use your body. If you push it from the left, You have to support with your muscles all the forces. And this is very, very, very important. So the idea that you can understand the energy that the human is using in performing tasks, now you can take that energy and apply it to the human, and you can simulate the human. I'm not going to go in all the details, but what I wanted to say is now we can help the human to do things that the human could not see. Because now we can analyze every subject and look at the characteristics of the subject and see how we are playing tennis, how we are playing golf. Anyone plays golf? Okay.
No.
I'm going to improve your golf swing, because the golf swing depends on the understanding of where are your maximum acceleration lines. And those acceleration lines are subject specific. So we can take the concept of analyzing, we track your motion, by tracking the motion, we can analyze the motion, and in real time, we send you back stimuli to make the correction. So you feel your hand pushed back or left, and now you can close this loop. But this is true also in therapy for injured. It's true. So the technologies of robotics is not only about helping robots, but really also about helping the human. So I want to complete the discussion about this, showing you that now we can go to very dangerous environment. We can go to those environment where there is slippage. We can detect the slippage, and we can plan the motion and get the robot to move even underwater. Underwater, there are a huge amount of fields that needs to be explored, and the human cannot stay more than limited time underwater. So technologies today are limited to just observing what is done underwater. We need to place sensors, we need a network of robots, a network of sensors. So we are building at Stanford in collaboration with Mecca and with KAUST, we are building a team of robots that can work underwater, but communicating, connected through a network of communication that allow this robot to autonomously work, interact with human. You know, this is like a spaceship moving to docking. And when you come with thrusters, you know, in space, you cannot dock without making big impact. But if you look at the arms of this robot, when it is moving, it's moving the arms are bending to take out the inertia. This is called macro-mini coordination. Mobility and manipulation requires very careful attention to the control structures that are being used. So robots like this should not be controlled by the human, should not be teleoperated. If they are teleoperated, you cannot do it. You have to do all that control on board and in the system. So at Stanford, we are building this robot. This is the robot we are building. We are building the hands. We are building very interesting designs with suction, because when you close their hands in underwater, the water moves and pushes the object. We are building the arm for underwater, and now you can use the environment to hook to that environment and perform very complex tasks using the robot. But this robot is connected to the boat. You remember, the boat is the place where the diver is sitting and operating the robot. And this robot is now performing very complex operation on its own, but at the same time, the human is monitoring, feeling, touching what the robot is doing. We are conducting all the tests underwater, and this is what the robot now navigation system look like. So you're sitting in the boat with your haptic device, and you're guiding the robot, you're telling the robot where to go, but the robot has all the autonomy to touch, to feel, to close the loop, and control all the different motions to produce those complex behaviors. So working with robots is the idea that we want an interaction of the human with the robot physically, so the robot is assisting the elderly to move, or the human helping the robot to perform complex tasks, and the robot has very high amount of local autonomy. This local autonomy is relying on all these skills that we acquired, so it is not anymore programming the robot in terms of joint motions, is programming the robot at task level, so we have a library of tasks that are being performed, and now this architecture allows us to interact in real time and create robots that are capable of going in the ocean, like surgery in the ocean, like the surgery, and we are able to interact with the robot on the ground. So the robots needs our help, but our cognitive abilities to program the robot in real time, underground in the same way, in the field, and in all these areas there is a creation of interaction at the highest level from the human with the robotic system. So you can take a look at this. This is quite amazing performance. This is a dynamic simulation of a system that is hooked to an environment without slipping, maintaining all the forces at the appropriate time with the dynamics. This is probably an Olympic performance for a robotic system, and it is quite amazing. This in fact is what makes the robot capable of truly interacting with the environment. Social robotics, again, is a very important part of the development, and we are building all around the world a lot of new robotic systems. This is ICAP. That was at the conference I organized in San Francisco for our robotics community. It's called IRIS, and at that conference we also have a lot of program of outreach for school students, and this little kid was interacting with a robot. Safety is very important. All these different aspects are also details of the hardware and the sensing abilities. The disastrous environment brings challenges that will show us we cannot completely have the autonomy, the cognitive level, the artificial intelligence of the robot is not going to solve all these problems. We cannot program like what we used to do with industrial robots, because the task is changing, the environment is changing. We cannot do teleoperation in the, like Professor Rovetta said earlier, this will involve too much coordination, too many things. What we are doing is we are developing robotic skills to a level where the human cognition can interact with those skills, and we create collaboration with human at the highest level possible. This is the human haptic visual oversight that is done by allowing the human to touch, feel when needed, and giving the robot all the skills it has developed so that the robot can perform those skills, and we can create a synergy between the human and the robotic system. Thank you for your attention.
I think I'll lower my first question, but this is a usual question. Why Google bought those startups?
Okay. I have no official explanation. I think Sergey and his partner were always interested in robotics, but I think there is a maturity of the field that is bringing Google little by little closer to this area. In fact, what is happening is with the mobility, the car, the smart car, and the Google Maps, you can see the beginning of going and exploring the environment and having cars that can self-drive itself. And little by little you see also technologies of assisting the human with more information. Google is really about bringing knowledge to human and extending the human knowledge through the net. Now, Google also realizes that humans are going to rely on more physical interaction with robots, because the technology of the future will bring robots to assist and work and live among human and help humans. So if you are Google and smart and realize that robots are going to be part of the support for human, then you would say, well, I better get into robotics so I can better support human. Because you are going now to be able to support robot through the cloud. The robot will interrogate like we do Google, so the robot sees something, what is this? I don't recognize. You can Google it, and immediately you get that information, and now you can better help human. So it is a loop. That is, we were looking at digital interaction, and now we are integrating the physical interaction, which is part of everything we do, we human.
Can I answer? Can I say that? Okay. I was 21st of February 2008 in Google, and I met Sergey Brin and also Megan Schmidt, which is the assistant. It was wonderful. I was like today, jacket, the tie, perfect, coming from Italy, very hot. But I found a boy like you, with your same color, dressed exactly like you are, with a young girl, not young, 30, 35, close to him. And I said, why? I am so nice at this man. Who is this gentleman? Then we spoke a little about robotics, because I was invited to show my robot. You must go to internet, by Google, you write my name, then you write Google X Prize, Google X Prize, and you find my robot there. Okay? And I spoke with him, and then we spoke about robotics, but very easily. And when they called him Sergey, I understood it was Sergey Brin. We have the day later on New York Times was the photo of my robot. So, first, Google is very interested in robotics with the future. Sergey Brin is a nice person, very young, very clever, with a good team. Third, if you want also to give a look to this name, like my name, Kati Rovetta. She is wife of my son. She works in the office of a lawyer of Google in Mountain View, and she's very good. And she is the head of the startup in Google. Yeah, that's my opinion, is that the future is going. Now, Google, it's not my reference, but that's the point, that robotics is living strongly and is increasing and changing. Excuse me, but it's a precision.
Yeah, I mean, as I said, Paige was a student in the AI lab, and he was working in robotics, and Sergey was as well a student in the computer science department working with Paige, and both of them were very interested in robotics. But I think there is something new that is happening with the technology. There is something that is bringing robotics closer to reality, and knowledge is needed. As we see here, the robots will not be completely autonomous in the next 10 years in terms of cognitive abilities. So they will need Google. They need to Google very often. Okay, other questions? Before we can have the more discussions later, but if you would like to ask questions before yes, please.
Can I ask you about methods? What do you want to use for teaching of robot, for decision of the problem, for design of intelligent control system? Because I think it is the main problem today to make an intelligent system. And what ideas do you use? What algorithms do you want to use? Okay.
So the question is about the methodology and how we build those skills and how we use those skills with the robotic system. So robotics, in industrial robotics, was based on control systems that were very simple. We do something called inverse kinematics. If we want to move there, we compute the joint angles. We are here, we interpolate between the two, and we move the robot. And we make some corrections using sensing. Very simple. Right now, what we are trying to do and what we have been developing was a robotic system that is not at all controlled through trajectories, but through performing of tasks. So take this and put it here. Yeah. So now you have a task level, and to build task level, you need to understand what are the constraints, what are the compliant motions, what are the contact, what is the compliant strategy, and all of this is abstractions that builds higher level primitives. So what we are doing, we are extracting those primitives and building libraries, and from those libraries we can go to the next level. So ultimately you can say, get me a cup of coffee. And that involves a lot of different things the robot understands without having to program anything. So the idea is, then you can speak natural language to the robot and say the command, and this command is decomposed into actions that are feasible by the robot. But to do that, what we are doing is we are looking at the human, and we are taking intuition and taking strategies from the human. The robot is different than the human, so we are developing the strategy, implementing them on the robot, but the robot has a model of the human. So when the two of us, we lift this, let's lift it together, please. So when we lift this, I have a model of his intention. There is understanding of the communication. There is understanding of so that model is also integrated in the robot control. The robot control is much higher level than
It looks like you use something like fuzzy logic for learning how to create trajectories. Yeah.
Well, actually, we do fuzzy logic is one technique to be applied, and we use a lot of. Yeah. Well, we use neural networks, but we are. Okay, you want to know? I'll show you.
Should we sign NDA?
No, you don't need to. I'll show you. I'll show you the brain. So we go to the motor control of the human, and we look inside the brain of the human. How can you look inside the brain of the human? Well, you need to use fMRI, right? You can look at the. So, what is the magic that makes a human capable of controlling all the muscles to move in coordination and hold an object? It's amazing. I mean, this coordination. We want to understand the coordination, so we go to the brain. But if you go to the brain and look at the brain, you cannot do much because inside fMRI it's so confined, so small, you cannot move. So what do? What we do is we create this haptic interaction, which is a virtual environment to stimulate the brain, and now you are sitting inside the fMRI, and you have this device that is allowing you to do very difficult tasks. So you can play tennis inside fMRI. You can do different complex tasks and while stimulating the brain. And now we can take that information of the brain and take the information about biomechanical and neuroscience information are merged together to try to understand the functionality of the brain, extract the strategies, and map them to the robot. There is a lot of work, but we should remember the robot is using computers and algorithms. Computer algorithms could be very, very efficient if they are founded on models. So we use a lot of models. We do not just use fuzzy logic and go to very low-level learning techniques. We use learning and fuzzy logics probably, or more abstract data and learning techniques at the highest level. At the lowest level, we make use of algorithms, dynamic models, musculoskeletal models, and we use all these models to produce those results. So in here, you see the brain activities, while at the same time we are recording EMG and recording the muscle activities and connecting the two together. A lot of fantastic, very, very challenging and very interesting development in those areas. But I don't think, I mean, there is a lot of details. If any of you is interested, I'd be happy to talk about this more later. But I'm sure we have a lot of questions, and Professor Rita probably also would like to say, yeah.
So, probably last question to Professor Khatib, and then I go to another presentation.
Thank you. Now we have, I think, now we have only one successful mass home robot. It's a vacuum cleaner, yes? All
Roomba.
families...
The Roomba.
Roomba, iRobot, a lot.
Yeah.
So what do you think? What is the next really mass home robot?
Yeah. So that was the same question the president of SoftBank in Japan asked me. You know the SoftBank in Japan?
Yes.
Yeah.
SoftBank just bought Aldebaran.
I know. So SoftBank, I was making a presentation, and at the end of the presentation he said, "So what is the next big thing you can?" And
I mean home robot.
Yeah, I understand. Domestic robotics. Yeah.
Domestic.
So the idea, I mean, this is a very important question. I mean, what is the commercial success and the large market that we can have in robotics? This question is a very important question, and I really think simple robot systems would be the most
for market.
electable to that category, the ones that will happen. I believe the next generation of robots will bring a combination of haptic stimuli, so you will be wearing sleeves, and these sleeves will communicate, convey information to you. You will be doing a little bit of exoskeletal wearing systems that will also assist you. I don't want to go in all the images and concepts, but essentially there will be a lot of human augmentation using technologies from robotics. Human augmentation. Human augmentation, it is like augmenting the capabilities of a human by wearing technology. So it's wearable technology that helps the human to do things. Haptic technologies that help the human to communicate not only digital images but also tactile images. So tactile means I can remotely touch. And this technology is available today. I mean, we have it today. So in the category of haptics, in the category of exoskeletal, in the category of exoskeletal systems, in those categories, we have a lot of new technologies. And I'd be happy to discuss more about those maybe later. But
thank you very much.
We should first listen to Professor Rita.
So we come back.
No. Oh, we can continue.
There is some time because we try to just make sure that we can actually.
All right.
And
so,
how many times do you think it will take to launch the product that you?
Yeah. So
I don't think that it's 2 or 3 years. It's maybe 7, no?
Yeah. Well.
In each home.
Yeah. Well, so there are multiple things. Ultimately, in probably 10, 15 years, we will have at home machines that can help the elderly to move. This is the companion. This is the concept of having a robotic system that is really capable of moving in the environment and interacting with human safely. So this technology is being built today. It will become commercial eventually, and people will buy it like buying a car. So you buy a car for your home, which is a robotic system. It's not going to be very, very smart, but it will be supporting the human. The other thing in production, you're going to have a new manufacturing that will use robot, not through assembly line, as it is the case today, but rather it will use robotic system, exoskeletal systems, haptic systems that integrate the human workers with the machines. So instead of moving and adding components, we are going to be able to have a worker that will receive the component and interact with the human. This is much more flexible, and you can, because programming an assembly line is very expensive. Programming assembly line means reprogramming it means a lot of money, and if you want to have different designs, it's very difficult to change your design. So now by doing this, we can make much more flexible environment. Then, so this is where we're going. In the midterm, in the coming years, we will see professional machines that are working more efficiently with a human. I think the future is going to be human and robot together. Human and robot together, where the robot is interrogating the human for guidance, and the robot is supporting the human. So I say, we will have the synergy of the robot muscles and the human brain. This is how it's. Maybe this is a good line for you.
How to integrate, do you think?
На самом деле непонятно все равно, как это придумать.
Very.
Good, we're ready.
Ladies and gentlemen,
This is what the European Union has been really successful at. So in Europe right now, there are a lot of different projects making that connection, and Professor Roberta's project was very successful in not only doing the connection between the different groups, but also to take it even further for development. I think the time is coming really late. I don't want to lose everyone. I think it's no. I mean, this is fascinating. We can spend all afternoon and discuss a lot of those details, but there is a very important model that is working and that is really important for innovation. And this model relies on a closed loop, somehow a full loop between research in academia that is relevant, connected to industry. So the industry is funding in part that research. That is also co-funded by government. The government sometimes is putting the seed funding. Seed funding means you start the project and then you attract more support from industry. This is a model that works very well. Worked very well in the Silicon Valley. We have been very successful with venture capitalist investing, but in projects that were started with the government funding. There is a transition that comes also through that work where a research development becomes mature enough to go to spin off a company. So from Stanford, most of the most famous world companies came, like Hewlett-Packard and Google, but Yahoo and many others. And there are 3,000 other companies that came out, but all based on really deep research. So shortcuts don't work. I mean, they work for the short term, but if we forget the research, the flow of new ideas and brain and innovation to companies, and then the support that is coming from the government, the country, and also the industry, the relevance, because the industry make the step, well, that's relevant, that makes money, that makes sense. That should really create that ecosystem that makes it work. And I think in Europe, this is what is happening with the encouragement of the European Union. There is a lot of support for projects that make that connection, academia, industry, and public investment in those projects. I think you are lucky in Russia. I mean, there is a part coming from the government. We should see more involvement with from industry, but we should also remember that industry should not look at research and university or academia as the place to do engineering. I mean, engineering should be done in a different intermediate level. We still need to do the research. We still need to get the researchers, but we should explore new concept, new products. Answering your question, thinking about all these things is part of that interaction. At Stanford, we create something in academia. What should be done is to create what we call the programs, industrial program, affiliate industrial program associated with university research activities. And that results, for instance, our department has 100 companies, 70 companies in Japan. A huge amount of companies are interacting, funding our research. So our research, Stanford receives like in billion money coming from industry and also from the government. Most of the government money is also in large projects and then go and filter back to the government, to industry. So I think there is no magic just from one side. It's not the government, it's not the university, it's not the industry. There is a culture that we need to develop. And this culture is openness from the university, academia to work with the industry, to listen, to see what is important, to see what is relevant. Openness from, reliance and really trust in academic research that would trust. Because 2 weeks ago I was in France in the Council of Research Strategic Council, where we are looking at those issues. I mean, the politics, how much politics, policies from the government, how much policies from the academia, and what is required from the industry. And I was in the innovation for industrial manufacturing section, and these are the same issues. Still, in Europe, we are discussing those issues. We discuss this in other countries, but these are the fundamental things. The triangle between industry, academia, and venture investment. This is where you can bring innovation and new creativities. I think I just said what but I'm sure you have a lot of probably questions that might really clarify what we mean. But this is something that needs to be done. Absolutely needs to be done.
Thank you very much. I think it's very, very important, and in Skolkovo Foundation, this will try to bridge all those three things. It's public policy and government, industry, and of course academia. That's what we're doing.
Don't forget that you have in Russia, you have a great Academy of Science. When I mean great, it really means great. I know, also Ossama knows a lot of people of your academy, great, best of the world.
Well, I mean, exactly to follow up with in the early years of robotics, the Russian advances, in scientific advances, really contributed to robotics in amazing ways. I mean, NASA make use of, and European make use of a lot of designs that came from Russian scientists. In fact, a lot of the basics in dynamics came from colleagues. One of my colleagues, Professor Klub, developed one of the first algorithms of recursive Lagrangian, and many things like that really contributed. And we know, I mean, we know how much progress that was made. I think there was a period of transition, and we were talking about this earlier. That was difficult for the science and technology in Russia. That was really difficult for also motivating the young generation to go to science and technology. But it seems now things are hopefully in a way that would bring back that attention and interest. Robotics is one field that is a lot of fun. I mean, kids love robots, and it is a great way to motivate science and technology. So I believe this is one of the good thing about robotics. But the government, I mean, the policy about research is much bigger than just what we're doing in robotics, and we really have to somehow develop that culture of interaction between academia, industry, and mediated by the policy of the government, but also supported by venture investment, and that is, I think, going to be really important. As you grow and you develop and you bring more areas and Russia is a big country. I mean, you have so many different areas and different quality of life also depends on those technologies, and you have so many other applications. In fact, I mean, if we start counting all the potential applications, they bring so many things that this is a multidisciplinary integrative technology, robotics, and it brings all these from medicine to education, to sport, to human quality of life, to support, to assistance, to all of these things. So I really believe it's happening. I mean, it will happen. There is no just question about what is next. We should not just look like 10 meters. We have to look further and make sure that we are building toward that future. And on the way, we have to have milestones and goals.
Thank you very much. I think we need to probably just time to exchange name cards, and if you like to give your contacts to our speakers, probably it's the best time. And then probably for us, it's meeting is closed. So thank you very much for attending us, and please join us again. Thank you.
Thank you very much.
Thank you for that.